Okay. Uh, this week we're going to talk about some applications of the things that we've been learning, and today we're doing derivatives and applications of derivatives. So we've got optimization and we have related rates problems are kind of the two main categories that are applied problems that we'll see in differential calculus sort of come in those flavors. We've also got approximation theory, but I think we spent quite a bit of time on Taylor approximations, and I think we were fairly comfortable with linear approximations and tangent lines. So I think I'm just going to stick with the optimization problems and the related rates problems for today. So sort of a side note, both of these types of problems are difficult for students because you have to relate quantities in an equation. And what do I mean by that? They usually come in a word problem form, and they have to translate that word problem into either a picture first and then an equation relating to quantities, or just straight from the word problem to equations. And this is kind of the number one thing I see as an indicator of how well a student will do in my class at any level, from algebra 101, remedial algebra like math 90, or even calculus, differential equations, higher level math analysis. If you can draw a picture and relate that picture to the mathematics, you're going to have a much easier time understanding the problem. So these two types of problems, related rates and optimization, are difficult because they require you to make that connection between, okay, what's going on in English, okay, let's translate that to algebra. Okay, so optimization problems, they have sort of a basic form. I've got two things. I've got number one, we've got a objective function. And this is a function it has a real output, an output that we want to optimize. And a lot of times this output will have more than one variable. Sometimes if it just has one variable, then we can just perform differential calculus and there's no sort of restriction on what those variables have to be. I can just find critical values and figure out, okay, at that critical value, is it big or is it small? Is it the biggest? Is it the smallest? That type of thing. But if it has more than one variable, I also need a constraint function or a constraint relationship. Okay, so for example, maybe I want to optimize a profit, and I can sell a certain type of, maybe I'm a restaurant, and I can sell hamburgers for this price, and I can sell hot dogs for this price, and my inputs for hot dogs and my inputs for hamburgers are slightly different. I want to maximize my profit, so how many hot dogs should I sell and how many hamburgers should I sell? And my constraint relation would maybe be something like, how much do I want to spend each day? Do I want to spend $100 at the grocery store each day, and I will sell all that I can, what relationship between hot dogs and hamburgers do I need to use to maximize my profit? So this constraint relation, it is a relation on the input variables so that we can reduce the function, the objective function, to a single variable function. Okay, so let's do an example. How far is the line, say x plus y equals 1 from the origin? Okay, and what do I mean by that? Well, let's draw a picture and kind of see what happens with this. So we've got x plus y equals 1, so I've got 1, 0, I've got 0, 1. This is a line, so it's going to be this line here. And here's the origin. What we want to do is we want to measure this distance from the line to the origin. And I probably, what do I mean by how far? Well, at this point, I probably want this closest distance when I'm asking how far is a line from a point. So this is an optimization problem because I want the smallest thing here. I want the smallest, or I mean, an optimization, you're usually dealing in superlatives. This one is the smallest. Okay, so let's think about what we need to do. We need the distance to be minimized. So our objective function should have distance as its output. Okay, what are the inputs going to be? Okay, so when we're doing this, we're trying to come up with functions. I need to identify what the output should be and what the inputs should be. And so these should all be quantities that are related or variables that I can use. So the distance is trying to be minimized. That means that there's different values that the distance could take on. What do those different distances come from? Well, I get different distances not because this point is changing, that's always the origin, but I get different distances because the points that I'm measuring on the line to the origin, those are changing. So for each point on this line, I get a different distance to the origin. The points on the line should be my inputs. Okay, so the distance function that I want to use is going to be d equals the square root of, well, x squared plus y squared. It's really x minus 0 squared and y minus 0 squared. And this is sort of restrained to, or constrained to, let's use constrained since I said they were constraints, to x, y being a point on the line x plus y equals 1. Okay, so just right there I came up with my objective function. Here's my objective function. And I have my restraint or constraint function. Right? So I need to deal with both of these somehow. And I want to minimize d with respect to being on this line that's this constraint line. Okay, to use calculus, I can't, well, I can take a partial derivative, but we'd never covered that. We can take derivatives as long as the function is in a single variable. We know what to do. But here I've got two variables. I can't very well take a derivative, set it equal to 0, and find my critical values. Okay, because, well, do I take the derivative with respect to x, or do I take it with respect to y? That doesn't work for me in this situation. So what I need to do is I need to use this constraint. This constraint tells me a relationship between the two input variables. And if I use that constraint, I can replace one of the variables in the objective function with some expression in the other variable so that I reduce the number of variables and just get it to be in x, let's say. We want d as a function of a single variable. And let's just say x. So we need to replace y with some expression in x. This is where we get to use the constraint. Well, it tells us y is equal to 1 minus x. So d is equal to the square root of x squared plus 1 minus x squared. And we're trying to minimize this. So I want to set d dx equal to 0, and that would tell me where it's minimized. So if I take the square root, that's going to be kind of a messy chain rule thing here. So we're going to play another little trick on this distance problem. If I square both sides, I get d of x squared is equal to x squared plus 1 minus x squared, right? And now I can still figure out what dx dt is, and I can still figure out when it's equal to 0 by just differentiating both sides with the chain rule now. So I get 2 times the distance times dd dx equals 2x plus 2 times 1 minus x times negative 1 by using the chain rule there. Okay, so let's simplify this a little bit. I get 2 times the distance times dd dx is equal to, well, this is 4x minus, no, plus, no, sorry, minus 2. Okay. And so I can divide by 2. I get d dx is equal to 2x minus 1. And so dd dx equals 0 only if 2x minus 1 equals 0, i.e. if x equals 1/2. Okay, so is that going to be a minimum or a maximum? Well, I could use a second derivative test, or I could just look at my picture and sort of, well, it's obviously going to be the minimum. We can kind of tell that, and this is going to be y is equal to also 1/2, since 1 is equal to x plus y. The point 1/2 then is closest to the origin while being on the line. And the minimum distance the square root of 1/2 squared plus 1/2 squared is square root of 1/2, or square root of 2/2. Okay. So we have a constraint, we have an objective function, and we use the constraint to make the objective function a single variable function so we can do differential calculus on it. Alright, let's see another example. This was sort of abstract in the sense that, well, there wasn't really any physical representation of what do I mean by this. It wasn't a real world problem. It's sort of a contrived, okay, this is a textbook math problem. Let's try and do another optimization problem. So let's say this is kind of a problem I've given some of my students in an algebra class, or I at least get them to set up the problem or write the constraint function in an algebra class. So Hermione I think that might be how you spell her name, sets up a stand at the Quidditch Championships. Selling Dragon Scale Ale. Her demand function, which relates the price to how much she will sell, is the quantity demanded. It will decrease with the price increases. So let's say it's 100 minus 3p. At what price should she sell the ale to maximize revenue? Okay, so we've got a demand function, and I would need a revenue function somehow. My objective function is the function that needs to be the biggest or the smallest or the superlative there. So let's look at this. Our maximize tells me that the quantity, the revenue, is the objective. Okay, so let's see if I can write down a revenue function. Well, revenue equals price times quantity. It's the price you sell it at times the quantity that you sell. So I should probably say R equals P times Q. And now I've got this function, it's got two variables. We need to reduce these two variables, and to do that we need to find a relation between price and quantity. Well, that's exactly what I gave you for the demand function. That gives you a relationship between price set and quantity sold. This means the constraint, that constraint function is going to be q equals 100 minus 3p. Okay, so this one's a fairly simple substitution. To get revenue as a price, I just take price times quantity, which is price times 100 minus 3 times the price. So that's 100p minus 3p squared is r of p. To maximize this, I would find the critical values. So r prime at p is equal to 100 minus 6p. So price to make r prime of p equals 0 is 100 over 6 equals p. So she should price these things at 16.6 newts or sickles or whatever currency she's pricing them at. Probably not dollars, but that would be another optimization problem that sort of is a little bit more real-world applicable. You have to think a little bit more about just, you can't really draw the picture for that one to optimize, or it's not a textbook, okay, here's a graph, do something with the graph type thing. Okay, but all optimization problems are going to fall into these categories. You've got an objective function that has certain variables as inputs. To do calculus, you need to have a single input variable, so we use the constraint function or multiple functions to reduce those variables into a single variable that we can do calculus on.